Anybody have any homework problems you'd like me to go over, explain any of? So I think the only homework I assigned last time was we've started talking about conservation of mechanical energy. And I just started asking, they weren't calculations, they were just like, okay, if you have a force that's in the same direction as the velocity, is the energy increasing or decreasing, that kind of thing. Okay, so we're going back to conservation of mechanical energy. And the two big things that we've defined so far were the kinetic energy that's capital T, we call it. I'm not sure where that T comes from, but you know, you only have so many letters you can use. So, and this is equal to 1/2 times the object's mass times the object's speed squared. And the thing to remember about this is an amount of energy an object has at an instant. Okay, so that's an amount of energy. The thing has that. It possesses that energy at a single instant. Work is a little different. That's the second thing that we've defined that's important. The work, capital W. And that is a change in energy. So that's not an amount of energy that a thing has. It's how much the energy changes over some time interval. So this is the change in energy over some time interval. That's caused by an applied force. Okay, so an object has an amount of kinetic energy, and that kinetic energy can change over time based on work that's done by different forces. And just to jog your memories, so if you had, let's say, an object with a velocity vector this way, and you apply a force to it this way, is that force going to be increasing or decreasing the energy of that object? Increase, right, because the force and the velocity are within 90 degrees. You know, roughly you can think of them as in the same direction. Maybe not the exact same direction, but they're roughly in the same direction. And so that means that work is going to be positive. And that means that the kinetic energy is increasing due to this force. What about an object that's moving this way? That's the velocity vector. And you're applying a force to it this direction. Is that going to increase or decrease the energy? So yeah, that's going to be decreasing because in this case, the force and the velocity vector are over 90 degrees apart. And so the work is going to be negative. And so the kinetic energy is going to be decreasing. And you can think of that in terms of the parallel part of the acceleration. So remember that speed is changed by the parallel part of the acceleration. In this case, the parallel part of the acceleration, the part that's parallel to the velocity, is going to be in the same direction as the velocity. So it's going to be speeding up. That's why the energy is increasing. The kinetic energy is increasing. Yep.
I got one question. For the first one, it doesn't look 90 degrees. Isn't 90 degrees?
Yeah, it's less than, so it's within 90 degrees. So less than 90 degrees. You know.
But it looks like it's more than 90 degrees.
Well, what you have to do is put the two tails together and then take the measurement.
There you go.
So in both of these cases, I guess it looks like the first one, if you just look at the angle that the lines make, this one looks more than 90 degrees, this one looks less, but that's just because the tails aren't together. Okay, and what about a case where the velocity is this way and the force is exactly perpendicular to it? So is that going to be increasing, decreasing, increasing or decreasing the kinetic energy, or is it going to be no change? This is going to be no change because, so the force and the velocity are perpendicular. And so that force is only, it isn't causing a parallel part of acceleration at all. It's only causing a perpendicular part of acceleration. And all that does is turn things. It doesn't change the speed. Well, turning doesn't have any effect on kinetic energy. Kinetic energy only cares about speed. So this has a zero work. And that means that there's no change in the kinetic energy. So intuitively, this stuff is pretty easy to wrap your head around, and I've given you a couple exercises, and I'll give you a few more about just sort of trying to get this built into your brain. But the difficulty comes in actually calculating the amount of work. So actually calculating the work. So remember that as an object undergoes a displacement, and we'll call this displacement the vector lowercase d. If, and this is a big if, the force vector is a constant f, okay, then in that case, the work is equal to the x components times each other plus the y components times each other. Okay, so in that case, you can calculate the work. But the problem is, there's no reason to expect the force to stay constant as the object undergoes its motion. So there's no reason to expect the force to be constant as the object undergoes its displacement. Okay, well, one thing you could do is you could calculate so I'll put this in parentheses. This is not something that you're going to need. I'm just going to show you. I think this will be enough to tell you why you'd rather not do this. The work is equal to the integral of the force vector dotted with an increment of distance dr. Okay, so you could calculate this. It's called a line integral, but it's a pain in the butt, and we'd rather not do that. Okay, that brings a lot of new difficulty into everything. So since we don't want to, use this. But it turns out that there are certain types of forces. So let's say luckily, or let's say there is a certain type of force where the work is calculated easily even when it's not constant. And that type of force is called conservative forces. Okay, so now we're going to talk a little bit about what conservative forces are. And so here is the definition of a conservative force. So calculations become easy if the forces you're dealing with are in this category, conservative forces. And the definition of this category is if knowing the object's location is enough to know the force then the force is conservative. You'll sometimes also hear conservative forces talked about as having a force field. So that's another way of saying conservative forces. So let's put this in here, force field. And really the term force field is a nice descriptive way of understanding what a conservative force is. So what happens when you're in a field of daisies? You know, like a field of daisies means wherever you go in the field, you can reach down and there's a daisy there. You know, they're just waiting for you to sort of activate them or whatever, you know, like, oh, I'm going over here. And then you pick up the daisy, like, go get a daisy over there. Force fields are the same way, except instead of daisies, everywhere you go, there's a force waiting for you. Okay, so you can see how that's kind of the same thing as what I said about conservative forces. You can think of these forces just waiting to be activated by the object going there. And if the object gets to this location, there's a force that's just been waiting to act on the object. Okay, So that's what a force field is. For us, there's only two force types that we're going to see that are conservative or that have force fields. So for us, there are only two conservative forces that you have to worry about. One is weight, so the force applied by gravity. And the second one is forces applied by springs. Okay, so let's take a second and try to understand how this works for these types of forces. Let's see. Okay, so this is, let's say this is the object, and you know what its mass is. Okay, so, let's say it's 1/10 of a kilogram. So let's first think about how the weight force, the force applied by gravity, is a conservative force. Okay, so if I tell you that this object is at this location, have I given you enough information to know the weight force acting on it? Yes. In fact, weight is sort of a funny one. I don't even have to tell you the location. The force is going to be 0.1 kilograms times 9.81 down, no matter where it is, right? But if you just look at this definition, knowing this object's location is enough to specify the weight force. Okay, so this is a conservative force. If I tell you it's here, you know the weight force. If I tell you it's here, you know the weight force. Okay. And then the other one that we're going to use is spring forces. So now imagine like a spring with a certain known stiffness, sort of strength, that's attached to the wall, and the other end is attached to this, okay? And imagine I stretch it out to here. There's some force that's trying to pull it back that way, okay? And we can calculate it. We'll talk about how to calculate it. But the key thing is that force, as long as I'm right here, no matter what I've done before that, that force is going to be the same if I'm here. So like if I just go straight from the wall and stretch it out to here, that's going to be applying the same force as if I stretch it out to here and then back and go back and forth a little and then end up at that same location. Okay, so telling you the location of this object is enough to know the force that that spring applies to it. Okay, so weight and spring forces, those are the two that we're going to deal with. And now, let's think about some of the other forces that we deal with all the time. So why don't those fit into this category? So let's first think about the normal force on this, okay? The force that the table applies to this, pushing up. Well, if I just set it here like that, at your first thought, you might think, okay, well, the normal force is just counteracting the weight force. So this location, maybe that is enough to know what the normal force is. But if I push down on it, the more I push down, the more I'm increasing the normal force. And I haven't changed the location of this at all. And so that tells you that no, the normal force from the table is not a conservative force. I can make it, if I pull up exactly equal to the weight, I can make that normal force 0. And if I put my whole weight down on it, I can make this normal force huge, So normal force is not a conservative force. What about friction force while we're thinking about sort of rolling or sliding along a table? Do we know the magnitude of or do we know the force vector from the friction force for this? Well, no, if it's sliding this way and gets to that point, we know the friction force is going that way. If it's sliding this way as it gets to that point, we know the friction force is going that way. So even though it's at the same, come back. Okay. Even though it's at the same location, the friction force changes based on what's going on with the object. Okay. So why do we care about what forces are conservative? Here's the reason. For conservative forces, we can define a potential energy function and I'm going to call this potential energy capital U. And this potential energy function, the key thing about it is that the work is equal to the negative change in potential energy. Okay, so let me show you how this works. Forces that are not conservative, non-conservative forces, they don't have, there's no such thing as potential energy for those. Potential energy requires the force to be conservative. It requires it to be a force field. Okay. Okay, so let's say if a conservative force has a potential energy of 50 joules at the start of the motion, and a potential energy of 230 joules at the end of the motion, then the first question is, what's the work done by that force? Over this interval? And second, has this force added or removed energy from the object? Well, for part A, we're going to use the fact. So, yes, question.
I was going to ask, if you're getting ready to throw something, that's storing potential energy, right?
So if you're getting ready to throw something, unless I knew more about the system that, how you're going to mathematically think about throwing something, there's no reason to think that that's a conservative force that you're applying to it, So a conservative force, if it's not a conservative force, there's no such thing as potential energy. But in a way, like if you say, okay, I'm not throwing it, instead I'm putting a ball on a spring and compressing the spring you know, then that's kind of the same thing that you're talking about. And since that spring force is conservative, you deforming that spring is building up potential energy that, like you're thinking, when you let go of it, turns into kinetic energy as it launches the thing. So that's not really a bad way to think about it, but remember that potential energy is only when you have conservative forces.
So you can't store potential energy like when you get ready to go ahead.
It really depends how you mathematically are going to describe the motion. I mean, like if you're going to think of your muscles as like a bunch of springs, and you're kind of a little bit doing the same thing when you reach way back to get ready to throw something. You're stretching out your muscles in a way that they're going to deliver energy to it. But overall, it's a little bit of a forced analogy. But the overall, kind of the way you're thinking about it has a element of truth to it too. Yes?
So something like a catapult would be a spring force, right?
Well, it depends how I guess a catapult with a spring, yeah, that would have potential energy. Or a trebuchet that is based on gravity, that would also have potential energy because it's a gravitational thing. Yep. And it's true that potential energy, like, kind of a way to think of potential energy is like you're getting ready to unleash this force that's going to cause some change in energy, So like if I lift my calculator up this table, lifting it up that amount of height is putting it in a position where now if I free it from the table somehow, push it off, or the table breaks or something, it's going to turn into kinetic energy. That extra height is going to turn into kinetic energy as it falls down towards the ground.
What about rubber bands?
From what?
Rubber bands?
Oh yeah, same thing. Yep, rubber bands, let's think of those as springs. They're a little harder to calculate because it's nonlinear functions instead of linear functions, but it's the same idea. Springs have potential energy, yeah. Any other questions right now? Okay, so it starts with 50 joules of potential energy. It ends with 230 joules. We want to calculate the work. Well, the work of this force is equal to the negative, potential energy at the later instant minus the potential energy at the earlier instant. That's what the change in potential energy means. So this work is negative 230 joules minus the starting potential energy was 50. And so the work is equal to negative 180 joules. Okay, so I just made up those numbers. Is that what you asked?
I was asking negative. Why is it negative?
Okay, so think of that as just a definition of this relationship between work and the change in potential energy. It just happens to be a negative there.
But it doesn't mean you're doing negative work.
Well, okay, that's the next question. It doesn't always mean that the work is negative. In this case, the work is negative, it turns out. But if we had started this motion with a bigger potential energy and ended with a lower potential energy, then we would have had the opposite result. Okay, so second, now that we've figured out that we have negative 180 joules of work, has that increased or decreased the kinetic energy of the object? Decreased, yep. So work is just the amount that it changes, so a negative means energy is taken away. So energy is decreased by this conservative force. Okay. Well, we only have two of these conservative forces that we're going to deal with, the weight and spring forces. So I just have to give you the the potential energy functions for those two. So for this class, our two potential energy functions are for gravitation. Potential energy is equal to the mass of the object times g, which is 9.81 meters per second squared, times the height of the object. Remember that g is positive 9.81. When we want it negative, we just put that in ourselves, and that's just to give it a direction. And h. So okay, at first thought, the height of an object seems pretty clear, but what are we going to measure the height compared to? You know, like say we want to calculate the potential energy of this calculator. Well, if it falls straight down, it's going to run into the table. So is its height 1 foot? Or is its height down to the floor, which is 4 feet or whatever, 3 feet? Or if you're thinking of some kind of absolute height, would it have to be to the center of the earth? Or to the sun? Or to the, you know, then you can just go on forever, the center of the galaxy, whatever. The answer is, in every problem, you can choose the height that you're going to call h equals 0. You just have to be consistent through the whole problem. Okay, so a lot of times that's what we're going to choose is like the floor or the lowest level that appears in the problem. Okay, but you don't have to come up with some absolute place to call 0 height. So that seems a little weird at first. If we're just putting in an arbitrary, like if it's valid to call the height here 1 foot and it's also valid to call the height 50,000 light years or whatever, how can we get the same answers for stuff? The reason is, if you look at this relationship between work and potential energy, all we care about are changes in potential energy. And so when you subtract the two potential energies, those arbitrary height choices just subtract off from each other. All we care about is how much the height changes. Okay. So that's our first one. And then our second potential energy function is for springs. And this is 1/2 times the spring stiffness K times x squared. So this K is called the spring stiffness, and that'll always just be given to you. That's a big number if a spring is hard to stretch, and a small number if a spring is easy to stretch. And x is the distance the spring is deformed from its resting length. So if you take a spring that's at rest, sitting there at its resting length, and then you stretch it an inch, that x is 1 inch. Okay, so those are our the only two ways you have to worry about for calculating potential energy. So let's do an example. And this is an example we've already done. So let's say that we have a 3 kilogram object that goes from a height of 5 meters to a height of 2 meters. And we want to calculate the work that's done by gravity. So what's the work done by gravity? Anyone remember doing this problem a couple classes ago? Okay, so do you remember what we did to calculate this before? What equation we used? So before we were able to use this one, remember, if the force is constant as the object moves, you can use this calculation. And gravity happens to be constant as the object moves, so we use that formula. But now we're going to do the same thing using potential energy, and we better get the same answer or none of this works that I'm saying, you know. Okay. Well, we're going to use the fact that the work is the negative change in potential energy. I'm going to choose my height equals 0 to be at the ground. So then my starting gravitational potential energy is the mass of the object times positive 9.81 times a height of 5. And we get, I think, 147.15. And then our second, well, I'll call this, let me change the name of this to U1. That's at the first instant. And then the later potential energy is the mass times 9.81 times a height of 2. And this is 58.86. These are both joules. And so now the work done by gravity is the negative change. So that's going to be negative of 58. 58.86 minus 147.15. And that's a negative of negative 88.29. And so the work done by gravity is positive 88.29 joules, which is what we got doing the calculation the other way. Does it make sense that work is positive as this object goes from a higher height to a lower height? Well, the object's velocity is down, right? Gravity is applying a force that's in the same direction as the velocity, and so that should increase the object's energy. And that's what this says. Okay, let's do another example. This time we'll use a spring calculation. So let's say that we have a setup with an object that can roll, and the mass of the object doesn't matter for what we're calculating here. And then it's connected to the wall by a spring. And let's say that this spring stiffness is equal to 250 newtons per meter. What that says is you'd have to apply a force of 250 newtons to stretch this spring 1 meter. And so the question is, what's the work done by the spring if the object starts at the spring's resting length and then stretched 10 centimeters, so 0.10 meters. Well, we're going to do the same thing we did again, except this time instead of gravitational potential energy, we're going to use spring potential energy. At the first instant, U1 is equal to, and all I'm doing is plugging these values into the potential energy function I have for springs. It's 1/2 times 250 times the distance that the spring is from its resting length. It starts at rest, at its resting length, so this is just 0 for the first part. And so the potential energy at instant 1 is just 0. And now at the later instant, it's stretched 0.1 meters. So U2 is equal to 1/2 times 250 times 0.1 squared. And that is 1.25 joules. So now the work is equal to the negative of the later potential energy minus the earlier. So that's negative of 1.25 minus 0. And so the work is equal to negative 1.25 joules. Okay, does it make sense that you can think of the spring's resting length as the position the spring always wants to be in, you know? So the forces are always applied to try to get the spring back to its resting length. So does it make sense that as we stretch this spring from its resting length to some other position, we get negative work? Yeah, because the velocity of the spring, the way I've drawn it here, is the velocity would be pointing to the left as we stretch it. The spring's trying to pull it back to the right to get it back into its resting position. So that would be pointing to the, what did I say? I did them backwards, didn't I? The velocity would be to the left. The spring force would be to the right. And so that spring force is slowing down the progress of stretching the spring out. And that's why we get a negative work. Anybody have any questions that pop into your head before we get into conservation of mechanical energy using the full equation?
You said we're stretching with the spring farther away from where originally was, and then it goes back.
Right. So the spring doesn't apply any forces to something when it's at its resting length. It's happy there, you know? And then no matter which way you deform the spring from its resting length, it tries to fight in the other direction. It applies a force in the other direction. So if you compress it, it'll apply a pushing force to try to get it back to its resting length. If you stretch it, it'll apply a pulling force to try to get it back to its resting length.
So our pulling force is negative and pushing force is positive?
The way we're going to do it when we start putting this in calculations is we'll just use a coordinate system. And we'll just say x is equal to 0 when the spring's at its resting length. And then we'll just use the thing's position as that x value. And then we don't have to worry about the negative that would show up then sometimes because in the formula that x is squared. So a negative number is the same as a positive number. So that's how we'll end up doing it. But we're just not there yet. Okay, so any other questions? So we're finally back to conservation of mechanical energy. And we give it this name by thinking of, so think of an object's total mechanical energy at an instant as its kinetic energy plus its potential energy. And so the conservation of mechanical energy says if only conservative forces do work on an object, then the kinetic plus the potential energy at some instant 1 is equal to the kinetic plus the potential energy at some instant 2. So this is, after 2 days of talking, this simple equation is what we're doing. But we had to talk about the other stuff to know when we can use this, you know, that kind of thing. All right, so let me give you a simple example of how we could use this. So let's say if an object falls to the floor from a height of 4 meters, how fast is it going just before it hits the ground? Most of the time in this class, when you see a question, there's only one approach that'll give you the answer that you know how to do. This is one where now, including conservation and mechanical energy, we have two different approaches that would work, and they would give you the same answer. What's the old way that we knew how to do a problem like this? You could do this with a 1D kinematics problem using the constant acceleration equations. So you could use the equation 2a times the quantity pf minus pi, blah, blah, blah. And you would get the same answer that we're going to get, but we're going to use conservation of mechanical energy. Okay? All right, well, I'm going to set my h equals 0 at the floor. And then I'm just going to write out sort of a table where the left side is the starting instant. So this is my instant 1. And the right side is my later instant, instant 2. So at instant 1, this thing is at a height of 4 meters. So my gravitational potential energy is the mass of the object. I didn't give the mass of the object here, so I'm just going to put that in as an m. We're going to see that it cancels out, meaning the answer is the same for whatever mass you choose. Times 9.81 times the height, which is 4. And so we get a gravitational potential energy of 39.24 times the mass. And now the kinetic energy at that instant when the thing is sitting there 4 meters above the ground, the kinetic energy is 1/2 times the mass times the speed squared. What's the speed before we drop it? 0, yep. So times 0 squared. And so this kinetic energy at this instant is 0. And then instant 2, where it's just about to hit the ground, the gravitational potential energy is the mass times 9.81 times a height of 0. So this is just equal to 0 at the later instant. And the kinetic energy at the later instant, we don't know the speed now, right? We're trying to find that. So I'm just going to leave that in here as v, and we'll solve for it. So this is equal to 1/2 times the mass times v squared. So I'll just write that as 1/2 mv squared. And now conservation of mechanical energy says add up all the stuff at instant 1. That has to be equal to the sum of the stuff at instant 2. So we have 39.24 m plus 0 is equal to 0 plus 1/2 mv squared. So I'll rewrite that as 39.24 m is equal to 1/2 mv squared. And now you can see we can divide both sides by m. Both sides are multiplied by m. So we get 39.24 is equal to 1/2 v squared. And so v squared is equal to 78.48. And so now take the square root of both sides, and you get that the speed is plus or minus 8.86 meters per second. We're just talking about a speed, so this is positive. Any questions about that? So that's just sort of the simplest type of conservation of mechanical energy problem we can do. But now that we think about, like, so I said this is the simplest this problem can be. Well, how much harder, how much more complicated can we make these problems? Because all of our forces have to be conservative forces, right? And we only have 2 conservative forces. So that makes you think, well, is the only other type of problem we could do something hanging from a spring and just see what happens as this thing moves around, you know? But here's the key thing to remember. So our allowable problems require that only conservative forces do work. It's not saying that there are only conservative forces present. So what that means is, so we can have non-conservative forces as long as they do 0 work. And so from the first thing we did in class today, and we talked about this last week too, what is required for a force to do 0 work? So look up here from this example. So when these are less than 90 degrees apart, work is positive. When they're more than 90 degrees apart, work is negative. But when the velocity and the force are perpendicular to each other, the work is 0. Okay? And so the work is 0. This is when the force and the velocity are always perpendicular. Okay, so there are 2 really important cases. So here are 2 important non-conservative forces that do 0 work. The first one is normal forces in rolling and sliding. And so if you think of an object moving along a ramp like this, its velocity is always going to be parallel to the ramp. The normal force is always going to be perpendicular to the ramp. And so since those are always perpendicular to each other, even though that force is there, it doesn't do any work. Okay? And there's one more common one like that. That's centripetal forces. Computer. In circular motion. And so if an object's moving in a circular path, the velocity is always tangent to the path. So if you have any force for whatever reason that is pointing toward the center of the circle, then those two are always perpendicular, and then that force doesn't do any work. So the best example of that would be like a string swinging something around is a force pointing toward the center. And so we can use conservation of mechanical energy in a case like that. Yes?
So does work only speed up or slow down objects?
Correct. And so, and think of it like this. An object doesn't actually have to be speeding up or slowing down for a force to do work. It's just, if that force were by itself, would it be making the object speed up or slow down? So like even something, so like here's an example. Right now, I'm pushing this object, right? But I'm pushing it with a constant speed, okay? So the force my finger is applying to it isn't actually speeding this up, okay? But since the force is in the same direction as the velocity, it would be speeding this thing up if it wasn't for friction fighting against that. And so the work of this force is positive, even though that object's speed isn't changing.
But then why do perpendicular forces not count?
Yes, because perpendicular forces, if they were on their own, all they would do is cause a perpendicular part of the acceleration. And remember that the perpendicular part of the acceleration only makes things turn. It doesn't change the speed. Okay, so so here is kind of like the too long didn't read version. We can use conservation of mechanical energy to relate an object's location to its speed when the forces are combinations of gravity, springs, normal forces, in rolling and sliding, and centripetal forces in circular motion. Okay, so this is kind of a guide to, like, if you look at a problem and you're trying to figure out whether conservation of mechanical energy is the way to go. This kind of tells you everything you need to know about that. Is the question asking you to relate an object's location to its speed? And then second, does it only have combinations of these four forces? All right, let's do one more example. So let's say that we have a skateboard at the top of a hill. And let's say this hill is 4 meters high. So if the skateboard is moving at 1 meter per second at the top of the hill, how fast is it moving at the bottom? Okay, I'm going to choose my height equals 0 location to be at the bottom of the hill. So that's what I'm going to measure all my heights from. What forces at some given instant are acting on the skateboarder? Definitely a weight force. And then what else? Yes, and then a normal force. And there's nothing else. Both of those fit into our category of 4 forces. And so since we're trying to find a relationship between a location and a speed, it seems pretty, we feel pretty good about trying to do this with conservation of mechanical energy. Okay? So I'm going to set up my little table that I always do. Instant 1 is going to be at the top of the hill. Instant 2 is at the bottom of the hill. At the top of the hill, the gravitational potential energy is the mass of the kid and the skateboard. I didn't give that, so we just have to hope that's going to cancel out. We'll see. Times 9.81 times 4. And so this is 39.24 times m. And then the kinetic energy at the top of the hill, it says that he rolls over the top of the hill at 1 meter per second. So this, for kinetic energy, is 1/2 times the mass times 1 squared. Or in other words, I'll write it as 0.5 m. And then at the bottom of the hill, the gravitational potential energy is m times 9.81 times a height of 0. So this all becomes 0. And then the kinetic energy, we're trying to calculate v, so I'm just going to write this as 1/2 times m times v squared. And we're going to hopefully calculate that v. So add up all the stuff in the first column we have 39.24 m plus 0.5 m is equal to 1/2 mv squared. On the left side, both of these have an m, so we can add those together. So this is 39.74 m is equal to 1/2 mv squared. Now we can divide both sides by m. And we get v squared is equal to 79.48. I just multiplied both sides by 2. Question? On what I just did?
I'm not very good at math, so
Okay.
I didn't understand
Well-
why you did that.
Yeah, all I'm trying to do is solve for v. So I guess I did 2 steps in one. I switched the sides of these two, and then I multiplied both sides by 2. And now take the square root, and you get v is equal to plus or minus the square root of that. And so v is equal to positive, since it's a speed, 8.92 meters per second. Any questions about that? Okay. I think the only questions I'm going to give you on the homework today are just a few more questions of thinking about directions, this force going this way, what's the potential energy, blah, blah, blah. So, but then on Thursday, we'll do some more of these kind of problems, and then I'll give you some full problems to do. Okay, that's all.